Okay, so good afternoon, everyone. So today we have this topic at hand, which is Internet of Technologies, and the topic may be very much familiar to you. Just like you, all of you, I am also a user of the convenience and the features provided by Internet of Things. So we'll just this session will be a what do you say, a sort of exercise to refresh some things regarding the Internet of Things, and we'll consolidate a lot of points, a lot of things you are already aware of. We'll try to consolidate these things and try to present it in a what do you say, organized way. That will be an approach. So as the cases, we'll just start off with discussing what is Internet of Things. What is Internet of Things? Can any of the participants say what is and what you term by Internet of Things? It would be very helpful if someone responds. So we are being attending to this online classes for the past 1 year. It has been 1 year coming week. So what is how do you define Internet of Things? Anyone? Can you say? You can put it in the chat box anywhere. Hello, is there anyone there? Hello. Internet of Things, how do you define Internet of Things? What, in your own words? We don't give a formal definition like that, what is meant by a cell phone. We say cell phone is something which we use to call. That's the best thing. Then you say it's a computer, like that. നിങ്ങളുടെ ഡെഫിനേഷൻ എന്താണ്? നിങ്ങൾ എന്താ പറയുന്നത്? ഒരു ഇന്റർനെറ്റ് ഓഫ് തിങ്സ് എന്ന് പറഞ്ഞാൽ എന്താണ്? നിങ്ങളുടെ ഒരു വ്യൂ എന്താണെന്നാണ് എനിക്ക് അറിയേണ്ടത്. യെസ്, ഹലോ. ദിസ് ഇസ് ജസ്റ്റ് ലൈക്ക് അവർ ക്ലാസ് കേട്ടോ. നമ്മുടെ ക്ലാസ് പോലെ തന്നെയാണ്. നമ്മുടെ ക്ലാസ്സിലേക്ക് ഇതുപോലെയൊക്കെ തന്നെയല്ല, ആരും റെസ്പോണ്ട് ചെയ്യില്ല. I don't mind calling people to respond. Okay, Mr. Balwant, can you respond? What is in your opinion, what is he left the meeting probably? Yeah, right, connectivity issues, right? Okay, there are a variety of definitions. Coming to say Internet of Things. Say your IEEE has a definition for Internet of Things. Say this is also a definition which is evolving, and this particular definition says it is a network of items, each with embedded sensors, which are connected to the internet. So always there is a connectivity to the internet. That aspect is very much involved in Internet of Things, and we are talking about anything that could be connected to internet. It could be a pencil, it could be a desk, it could be a car, it could be anything, machine, anything that could be identified over the internet. Again, there is another definition which you find in the Oxford Dictionary. Say I have given the references there and below the footer. So it says interconnection via internet of computing devices embedded in everyday objects, enabling them to send and receive data. So some points which need to be stressed is that they are connected to the internet, they are embedded within some objects, and they can send as well as receive data. So send in the sense sensors and actuators, both are there. Both are two fundamental aspects of this Internet of Things. You have to sense something, as well as you will have to make some actuations. For instance, you need to control you need to sense the temperature in a room, then and that is the sensing part. Over the internet you are accessing this value remotely, and then you need to control, you need to turn on the AC, or what do you say, reduce the speed of the fan, increase the speed of the fan, whatever. So that is the control aspect. So you could have relays, optocouplers, anything that could be used to actuate. So both these are there. Actually, the definition is ever evolving. You can add your own version of the definition of Internet of Things. You can go to this link iot.ieee.org/definition. You can give your definition, what in your way, what in your, there is a discussion, is a thread which is going on there. If you go to this link, you'll find a thread which is active for the past few years. A lot of people have made suggestions to this based on this particular document, and it's evolving. And there are different companies also have defined internet in their own ways. Gartner is a survey company. They have defined internet in a much more longer way, involving the commercial aspects as well. Okay, whatever be the case, internet is something which we all use, and which is used to connect things to the internet. Now the milestones, if we check the milestones, these are the some significant steps in the history of Internet of Things. So most of you might be familiar with other things, familiar with the history of the internet. You are familiar with the history of the internet. It started with the ARPANET, the ARPA project, which used to run in the 1960s, and then you had the commercial internet services in 1980s. India had to wait still longer, maybe towards the 90s, 95, 97, those times the internet showed up here, and it was a very precious commodity. I remember for 1 hour we used to pay 1 hour or half an hour of internet, we used to give 60 rupees in a public cafe, and it was a dial-up modem there. Then we had ISDN services later on, which was much faster, but the cafe people will used to have say 10 or 20 computers on that line. Then came the DSL. Now we have fiber to home. We are talking of 5G in the wireless side. So it's coming up. It's internet has become pervasive. It's everywhere. It's accepted as a thing of life. The first thing everyone does in the morning, before brushing the teeth, is checking to their WhatsApp messages. Probably that might be the first thing people do nowadays. Especially we caught up this habit in the lockdown time, right? So the key here is that we have more IP addresses than the total number of human beings in this world. As of now, we have switched over from IPv4, which was a standard which had the address space exhausted. We got exhausted of the available address space, and because it was a 32-bit addressing scheme, and we never thought that we will have this much devices, all those things connected to the internet. Now we have switched over to a 128-bit address with a lot of complications and a lot of advantages, and we have both of them coexisting. There is a lot of things which help to translate between the IPv4 and IPv6. That happens. So we, even without us knowing, the operating system, all those things, the routers, all those things, they take care of all these things. We are all these things are kept hidden from us. So these are the key milestones. In my view, these are the key milestones. We use GPS, we use IPv6, we use internet. Okay. Now this particular machine, this particular CoAP machine. Am I with you, or you are with me? Yes. You are on the slide which shows a CoAP machine. Yes. Yes. Okay. Right. I just need to ensure there could be connectivity issues. That I just wanted to make sure people are with me. So this particular CoAP machine was the first object or a thing which is connected to the internet. The story goes like that. That is, it was in Carnegie Mellon University in US. So there was four lazy students, you can call them lazy, but they came up with a very good idea. So they had this Coca-Cola machine all the way on the fourth floor of a building, or the department building, and they used to climb up all the way the stairs till there, and they find that in a hot summer day they used to find that either there were no Coke bottles, or it has just been loaded. It wasn't cool enough. So they thought about some way to find out whether how long the bottles, whether any bottles are there in the machine, Coke bottles are there, plus what time it was loaded, how much duration has been elapsed since it was loaded into the machine. So they put up micro switches there, all this jugaad electronics, what you call, say like that, but it was a very clever way. And those times in the 1980s, the internet was restricted to few universities, few prestigious universities. It was not commercialized fully, and they linked up with the ARPANET thing, and they could send a command, finger Coke at CMU. They could just put it on the Linux terminal, just find out, you could just search this. You could just make a keyword search, CMU Coke machine, and you will get this link where the history is outlined. So there are several versions came up. Now this particular machine is an old photo. I found it on the internet. This is the same machine. There is another snack machine which is there recently. Which was developed by some other batch later on. So this particular machine was maintained by the subsequent batches. Now they fell into disuse because the Coca-Cola stopped the old glass type bottles, the glass bottles. They have cans now. Now anyway, then we had toasters, webcams, all those things, coffee pot, all those things. And the LG was the first company which came up with a commercial product like internet refrigerator. It was a very expensive thing, and people didn't find it really interesting also. It flopped the market. Now nothing flops. People will ask you whether your car is connected, whether your fridge is connected. It is taken for it's assumed that everything will be connected. Everything is connected to the internet. So even your paper notebook, if you could connect it to the internet, that was fine. That's what people think. Technology, people think very crazy. I see outside, I see a coconut tree. You can dream of a time when all these coconuts will have RFID tags, maybe. Okay, so you will know the status, right? So this particular man, Kevin Ashton was the guy who coined the term Internet of Things. So it can be regarded as the father of internet. So he was a pioneer in the sense he was working with very crazy people. He was working in Procter and Gamble, and he was a middle level manager there, and he had to sell a particular idea to his boss, to the big guys, and they had a meeting there where the idea was that this RFID tags could be Procter and Gamble or P&G, what you know, the abbreviated Vicks, all those things, the company which markets all those products. They wanted to use some technology to identify whether some product what is the status of the stock of a particular product in the stores. So whether say Vicks or you say Fruity, Pepsi, all those things, how much is the quantity in the stores, and they need to link it with their supply chain. It was a logistic issue, supply chain management issue, and he wanted a very catchy term which could be so everyone knew what is internet, and internet at those times, just like we all used, they used to get a disk which had the dial-up modem, dial-up software, and you used to put in your computer. Then you used to use a dial-up connection connected to the internet. Now he came up with the idea of using RFID tags. RFID tags, those days it was very expensive, and he sold this idea. In fact, those time the Gillette Presto, all those things, the Gillette was a separate company from P&G. So Gillette funded this, and he founded this particular lab, which is called as Auto ID Center in MIT. He got funding from Gillette, set it up. They came up with RFID standards. They are pioneers, in fact, in this Internet of Things domain. And now there are Auto ID labs. I think there are 7 centers of Auto ID labs in different parts of the world: Australia, Korea, none in India, sure. So US, London, all those places, they have Auto ID labs, and which work on different parts, different domains, hardware as well as software, RFID, electronic product code, all those things. So they are standardization body. So a sort of standardization body. It is an industry funded initiative. So Auto ID labs, do remember, Auto ID lab is a good place to work as well as do research. There are quite a few Indians who are in key positions in Auto ID labs. Do go up their page, have a look. Okay. So the question is that why do we need to connect? So it seems everything can be connected to the internet. Why do we need to connect? Is there any purpose connecting a water bottle to the internet? So the answer is the why we need to connect, the purpose, and also the outcomes. Say, connecting a stone to the internet, does it serve any value? No. But if it is a diamond, it's worth. You can track the diamond, right? Connecting an ordinary stone which is lying somewhere doesn't mean anything as of now. Maybe in future it might. But coal, connecting a wagon of coal to the internet and tracking its movement is really significant. How it is transported all the way from the mines to the power station, that matters. So the purpose and the outcomes really matter when you talk about why we need to connect. So there are different flavors of Internet of Things. In fact, everything does the same thing, but it depends on your applications. So it depends on how we are using this final thing. That's the outcome. So most of us are exposed to this consumer Internet of Things, as well as we see student projects in the medical Internet of Things, say sending this heartbeats over the GSM, all those things, health application app, all those things are BTech level projects which students do. But a lot of research does happen in those things. Say real time, how could you send this data to the telemedicine, all those domains. There is a lot of work going on. So in fact, when 5G really comes, you will have the surgeon sitting in US and doing a surgery by a robotic arm, which is in India. So the patient is in India, there is a robotic arm, and there is near real-time synchronization of whatever he does there. He might be using a joystick to control the robot. So you might be putting the virtual reality headset to see it's not a thing of the very distant future, it is a near future. It is going to happen in near future. So, and again, the energy Internet of Things, that is what we have with relevance to this course. So it's application of Internet of Things in the energy sector, the power sector, because energy doesn't involve electricity alone, it involves a lot of other aspects. So we have, as usual, say the application of Internet of Things in the military domain as well. We are talking about soldiers of the future wearing all these sensors. They are sending their physical signals, say your heartbeat, all those things, biosignals. They are in fact acquiring signals about the environment there. You have potential for chemical warfare. You're tracking these things. You have drones flying around. The battle of the future might not be very It won't be like a World War I or World War II. Let there be no wars, but ultimately people will pick up fights. So the technology has we devise a lot of technology for military purposes. In fact, the internet evolved from the to need felt by the Western powers to protect their networks from attack from the Soviet Union. So they need a robust network. So that's why you have the packet switch network. So so some way or the other, your message will reach somewhere. Say launch a counterattack. You don't have a dedicated path. Your message goes through n paths, so you ensure that some channel is left. So anyway, coming back, we see that that we could put it into 4 heads, that is consumer, enterprise, industrial, and infrastructure applications. 4 broad applications could be found out. So we are seeing a boom in all these areas, and in the distant near future we will see more of use of this industrial Internet of Things and infrastructure Internet of Things, use of Internet of Things in both these domains. Okay, so these are some of the statistics. They say that in 2020 there were 12 billion IoT devices worldwide, and it's projected to grow to 55 billion. These are projections. In fact, COVID-19 and the response to COVID-19 is brought up a boom in the Internet of Things quite a lot, because you're talking about remotely monitoring patients, remotely monitoring situations, all those things. You had a lot of funding. The keyword is the funding keyword now is COVID-19. So some time back you used to have a lot of funds. People used to talk about safety, say disaster management. So it depends on a lot of media hypes are there. That's what my personal view on that. So a lot of people will say we had so there is a attention or interest generated in some domains depending upon the need of the hour. That is what. So the data is ever growing. So there is and a major portion of this data will be the video data, surveillance data. You go anywhere, you are going to see CCTV cameras, something, or video, audio. All those things are acquired by different ways. All these are traveling over the internet to the servers. They are stored somewhere ultimately for processing, analyzing, gathering information. So the big data doesn't mean anything unless you have proper analytic tools are applied to this. Okay, so we come to the formal part of this topic. It's architecture, the IoT architecture. So IoT does have a formal architecture. In fact, a lot of so this particular image is say I'll just comment on this. Anyone knows this place? Anyone knows this place? Yes. Anyone knows this place? Yes. Hello. 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 Are people there with me? Yes. Hello. Being working. Okay, so we'll just we had completed a section, in fact, without knowing that the class was not with me. Okay, So we were discussing about architecture. So and we know this traditional OSI model where you can hear me. Yes, right? Yes. Okay. Yeah. Yeah. It's much clearer. Probably. It should be much clearer this time. Right. Right. So this is the traditional OSI reference model, which never took off really, because it was having the 7-layer proposed due to a lot of political considerations. They were not having any idea about this, what these layers were doing, especially this presentation in the session layers. But they included it because some countries wanted that layer to be included. Anyway, we have this application layer which is directly related to the user. The user uses this application layer to communicate to the layers below. Say maybe the application layer is a web browser, or it could be WhatsApp, file transfer protocol, anything. And the session layer, presentation layer, all those functionalities you can read about somewhere. The transport layer is concerned with end-to-end transport of this message. The network layer is conveying it to over the network. So they were also vague as to what these layers do, the framing, the physical layer. But actually, these are very well defined in your TCP/IP suite, which we use, TCP/IP protocol. TCP/IP protocol, we have a physical layer and the data link layer combined as a network access layer. So it could be Ethernet, the network layer could be Ethernet, it could be your GPRS, it could be your 4G connection, it could be an optic fiber, it could be micro link, whatever it may be, it is all concerned with this layer. The only thing that is known to the layer just above is that this particular layer below is providing some services to the upper layer. So how it is done, that is not a botheration of the layer above. So that's why this third point, you can separate the services from the implementation. Then in this IP layer, you have the internet protocol, IPv4 and IPv6. IPv4 and IPv6. So IPv4 was, then other support protocols are there in this particular layer, but the key two protocols there are Internet Protocol version 4 and Internet Protocol version 6. Then the transport layer, the transmission control protocol, and the UDP, TCP and UDP. These are two transport layer protocols. So transport layer is concerned, so for instance, you are connecting from host A, the computer A, to computer B across the internet. It's the duty of the transport layer, it's the responsibility of the transport layer to ensure that the message is conveyed from A and it is directly delivered to the B's network, and specifically exactly to the machine B, not to any other machine B1, B2, B3 like that. It is delivered to the correct machine on the correct network. That is the role of the transport layer. And again, the applications, you have different applications, FTP, HTTP, all those applications they run on the application. That is what having interface with the user. So just as we have a layered architecture, we have a IoT also has a layered architecture, which is very key to the working of the Internet of Things. So we have several architectures have been proposed, but they have not been able to come to a conclusion as which is the best architecture for Internet of Things. Rather, you have specific characteristics of Internet of Things where you have power constraints. You are not having Internet of Things devices, most of them connected to a power mains. They will be battery operated environments. They have very less memory, very less small CPUs. So all these things ensure that we need to have internet features, plus you have all these constraints. So actually different architectures were proposed by researchers. I don't think the IEEE or any other formal bodies have proposed any architecture, but the architectures are 3-layered. So most of them, they are based on the application side, how the Internet of Things is used. They have designed, several researchers have proposed these models, and we'll discuss this 5-layer model, and that should make the things clear. I even came across a 7-layered model for Internet of Things. So basically the lower layer, or the perception layer, or the objects layer, includes this sensors and actuators. So this is concerned with acquiring data acquisition layer. It acquires the data, and maybe the data is in analog form, the temperature, it digitizes it, and it is ready to send it to the next layer. So it need not even digitize it. It can send as a modulated signal, analog signal. That's also there. So you may be knowing it as in the electrical domain, telemetry. So data acquisition and telemetry. So that's what. So this is the layer which is concerned with data acquisition. Sensors are there, actuators are also there in this layer. Then the object abstraction layer. Object abstraction layer is concerned with transporting this data acquired to the application layer via the service management layer. And different technologies are there. You have Wi-Fi, Bluetooth, infrared, Zigbee, variety of other 3G, 4G, GSM. So all those things are there. RFID. RFID is the first thing, a technology which is concerned with machine-to-machine communication. So you have, for instance, you have a FASTag in the area. FASTag is put on your car, which is a machine, and your RFID scanner is another machine. So this is a machine-to-machine communication, M2M. So we mentioned about Ashton, where so M2M, this is the first thing. RFID is the first M2M thing. So machine-to-machine communication. So there is also a business to machine. All those different terms are defined. So ultimately the machines will talk to each other. That's what is happening. And the service management layer. Service management layer is, you could call it as a middleware. So this is really concerning isolating the programmer from all the complications below. It just provides the programmer a feel that he need to know anything about the underlying hardware. You can write some code to acquire data from a particular sensor. The middleware or the service management layer will take care how to convert it into the particular protocol, the commands, and send it, and also the data. So it provides data acquired can also be coming in some format. It is presented to by the middleware to the application layer, the user, in a presentable in a format which could be easily interpreted by the user. Right. Again, you have the application layer, which is the way we most of us interface to the Internet of Things. So this provides the services requested by the users or the customers. And the layer above, you have the business layer. Business layer is the commercial aspect of these things. Whatever data you have acquired, whatever information you have, it has value only when it is processed and converted into an information. Information is the processed data. So, and you say you develop. So we have the data about the status of generators and the distribution system, the transformers, they are in the network. So this is the thing. This is the demand and this is supply. And your dispatch center, the load dispatch center, has to take a decision. All those things are presented there. So we'll discuss about that after a while. Okay. So so this whatever data acquired has value when you decide, the management decides what to do, right? So we go to the next step. You see the slide on blocks, blocks of Internet of Things. Yes, right. Building blocks of Internet of Things. We'll just go it very fast. Say there is a formal structure with 7 layers, seven different distinct components. So the key here is identification. The first thing is you need to have an addressing format for the object or the thing which is sent there. You could refer this in two ways. You could have an object ID. You say it's a sensor 1 or temperature sensor 1, T1, like that. That is an object ID. But Along with that, in Internet of Things, the object should have a unique address within the network. So that is provided by your Internet Protocol version 4 or version 6. That is one way to provide this IP address. Along with that, there are some other. So regarding IPv4 and IPv6, you just read about that. It is a 128-bit address we mentioned in the beginning slides. It's already rolling out. Actually, the IPs are assigned by the internet registries, regional registries, RIRs. So as of now, the IPv4 space is exhausted, all except African NIC, regional registry. All other regional registries are exhausted the addresses available in IPv4. IPv6 മാത്രമേ ഇപ്പോൾ allocation ഉള്ളൂ. Only IPv6 is they are available for allocation. Okay, so that's the aspect to this IPv4 and IPv6. Then again, electronic product codes. Electronic product code is 96-bit code, and it can be linked with an RFID, or it could be just in text format. So whatever your fast tags, all those things they would have a unique code linked with them. So that's why your vehicle tag ID, the fast tag which you use on your highway, so it's becoming say if you travel on NH66 towards Thrissur side, you will come across 2 toll booths, one in Arur, Kumbalam, and the other one Palikara. 2 toll booths, at least in Kerala there are two of them. You require a fast tag, so or else you pay double the toll. That's it. And again, U code is something which is really coming up. It is a matrix code. It looks almost like what is a QR code. So this is the format for EPC. So these are all standardized by this EPC Global. BPC Global is in fact an outcome of the Auto ID Center. So they are standardizing, bringing up standards in EPC Global. So this is a subsidiary. EPC Global is a subsidiary of Auto ID Center. Okay, and this U code, Ubiquitous code, is pioneered by a group in Japan, and this is the U code. It looks more like your QR code scan. This is a matrix code, in fact, even though it looks more or less like a QR code. So you can go to this link, uidcenter.org. So this plant is being given a U code. It's identified over the internet. So different ways to identify the thing. So that's one aspect of the Internet of Things block. Then the sensing aspect, sensor aspects. Most of us would have come across all these things as well as this, at least some of these. Our homes may not be as smart as this, but at least Google Assistant or Alexa would be around in quite a few homes. So they are listening to what we talk, whether it is required or not. So you have internet TVs, all those things, Android TVs, whatever. So all these things are connected. You are talking about a smart home. So and these sensors, at least some of them you would have come across in the student projects. So most of them come from China. Okay, and you name anything, you have a sensor for it. Okay, so the sensing as well as the actuation is another aspect of sensing. Actuation, relays, optocouplers could be used for actuation. Then you could have motors, micromotors, different ways. All these things are actuation. You can even talk about say industrial Internet of Things, where you can control industrial grade things like robots, etc., over the internet. Okay, so as of now, we'll say the PLCs, the programmable logic controllers, all those things are, due to various reasons, they are not directly accessible over the internet. There are however ways to do that. Okay, so again, the communication aspect is really coming like this. You have various technologies which are in the communication field. Say it's beginning with RFID, near field. Some phones do come with near field where you just need to say to pay money at your checkout counter in a, for instance, in a supermarket. So instead of using your ATM card or your debit card or credit card and then punching in your code, you just need to show your phone nearby. NFC payment enabled POS terminals are available. Wi-Fi is ever present. Then LTE is a long-term evolution. You would have come across VoLTE, VoLTE, voice over long-term evolution. All these things have a commercial aspect to all these terms. So 4G evolution, 5G. It seems 5G hasn't really come up. The 3GPP is still working on that, but they have frozen the standards to some extent. We'll talk about each of these communication technologies, except Wi-Fi Halo, Bluetooth, and some UWB. We'll talk about these things. Okay, so maybe also we won't discuss. You could check up those things. Okay, so this is the arena where we have the Bluetooth. Yeah, this is very familiar to you, Bluetooth. Then the Bluetooth low energy. Are we there together in the class? Yes. Some, yeah, right. So this is Wi-Fi. Then the Z-Wave. Z-Wave is a variant of the Zigbee. Zigbee is also familiar to you. Zigbee is having low data rates, 250 kilobits per second. So this is a much more enhanced way, enhanced format of the Zigbee protocol. Then the NFC, then 6LoWPAN, that is the IPv6 over wireless personal area networks. So it's then your 5G. That's what the LTE standards. So the then the LoRa. LoRa is really a upcoming technology which is useful in a lot of ways. We'll see how LoRa can make Internet of Things much more pervasive, much more common, especially in the industrial sector, the control, all those things. Okay, Halo is a standard which is closely related to this 6LoWPAN, or it's coming up. The technology which is coming up really. So this is a summary of whatever the things are there. So we have the cost as well as the data rate. We take decisions based on the cost performance trade-off. That's what. So and the range, the transmission range. So if you have more range, means you will have less data rate. You will have to sacrifice something. That is what is. If you take the case here, say if you take Wi-Fi, this is having a high data rate, but the range is less. But if you come to LoRa, the data rate is low, but the range is almost 10 kilometers. You can say 10 kilometers. In the cities, you will get not even 10 kilometers. The vegetation, everything is going to get you only 3 or 4 kilometers, but it's far better than Wi-Fi. But the data rates are very low, very low. So Bluetooth still lower. Data rates are there. BLE is giving you much more better transmission. Zigbee could be regarded as a trade-off between all those things. So actually the mobile phone companies are also investing in Internet of Things. You will see NB-IoT, narrowband IoT. So that is really being deployed also in India to some extent. Some companies have, especially we'll see how BSNL has rolled out narrowband IoT. Okay, right. The next is the computation. So computation has two aspects. You have both the hardware aspect as well as the software aspect. at least you would have come across some of these hardware. You would have those things in your labs as well. Okay, your ESP, Node MCU things. Then you have the Texas TMX device. Then this is Raspberry Pi Zero, then Raspberry Pi, BeagleBone, then Arduino Mega. That's what. So some of these boards some of them are industrial grade things. They're BeagleBone. BeagleBone is a line of products which is really industrial. BeagleBone in different families are there. You don't have a very cute GUI like programming GUI like GUI OS like Raspbian, which is usually used on a Raspberry Pi. You have a command line structure for this, but it is really, this BeagleBone is a good thing for Internet of Things, industrial applications. Okay, the key requirements while you choose hardware for IoT applications, you go for, take a look at the computational power available, your requirements. You are not going to run an image processing thing on an Internet of Things device, but you have hardware which can run some things to some extent. Again, your data storage or memory requirements, the power requirements, you're going to run it on a battery environment, means you will go to use a small thing, small chip, whether it is, you're just going to acquire the sensor data, you're not going to process it there, you're going to just transmit it, you'll go for a device which has such a feature. Then RF connectivity, we mentioned about what all communication technologies are available, all these things have to be considered. Then the security and encryption, that is very key there. The data privacy, especially very sensitive data is being transmitted, acquired and transmitted, means you have to be doing some encryption on site on the device itself. So AES 128 is one feature which is provided by a lot of IoT devices. There are proprietary solutions for this. Then some IoT boards will have onboard sensors, ADCs. Say ADC is a drawback of Raspberry Pi. You don't have an onboard ADC or Raspberry Pi, whereas your Arduino boards, they have an onboard ADC, but they lack internet. They don't have a Wi-Fi connection. You can put a Wi-Fi hat or a Wi-Fi module on top of that. So that is add-on modules or hats. That is another feature which we consider. You just don't blindly choose an hardware, but we need to consider those things. It's all this all familiar to us. So are we together? Are we on the slide on components of IoT? Right. So this has the 6 components. So we talked about the connectivity. You could have different forms of connectivity: USB, RJ45, your Ethernet, and RF. You could have Wi-Fi, Bluetooth, LoRa, Wi-Fi Max, whatever that could come up. Optic fiber. Optic fiber is another solution which is really good for various applications. Say especially very harsh environments, you could use optic fiber. Then the memory available. We could talk about volatile memory and non-volatile memory, RAM, ROM, that's what. And again, multiple programmable or one-time programmable memories. Then you could talk about adding external flash memories. You can say your pen drives, like things, the NAND or NOR type devices, and eFlash, then DRAMs, dynamic RAMs, then eMCC. So this is all the interfaces to the memory devices. Then the CPU, most of the IoT boards, you'll say hardwares, they are ARM core based devices. Most of them, I don't say all of them. There are other variants also. Intel is having a Intel Atom X6000 series, which is configured for IoT. Then A20 All-Winner series, that is also running on ARM-like architecture. So there is the CPU, you take that into consideration. Then again, the audio video jacks, audio interfaces, HDMI, video connectors, the USB-C type. It can take data, power, everything. C type, it charges faster, okay. You could send power, data, video, audio signals on C type, USB-C. Then GPU, say one graphics processing unit. You will come across the NVIDIA Jetson series where say we are talking about automated cars, self-driving cars, or video processing applications which are done on the device itself. You need computing power. You are talking about deep learning, all those things. You have some say for instance, your self-driving car has to take decisions on the near real time. You need to do lot of image related calculations. So you can use specific boards, say like the NVIDIA Jetson series. You have Jetson Xavier, that is the latest, that is much more powerful than the Jetson Nano. So availability of GPUs. Then so a graphic processing unit, dedicated graphic processing unit. These are much more smarter than, efficient than the CPU in handling what do you say, the maths related to images or video. So and again the interfaces, IO interfaces, UART, SPI, I2C, control area networks, all those things are key components. So that is regarding the hardware. The software side, you could classify them into four actually. Four, you have operating systems. Operating systems, basically real-time operating system. Real-time is having two variants, you can say hard real-time and soft real-time. Real-time means you need to, for instance, the ABS system, anti-lock braking system in your cars. Some cars provide it as a extra feature. Maybe in future it will become a standard feature, just like airbags. So ABS has a very specific time constraint. It has to respond within this time. So the real time could be hard real time or soft real time. So it is not responding after 1 hour or few minutes. So it depends on how your application need is. So real-time operating systems, different real-time operating systems do exist for IoT applications. One is TinyOS. This is the first one, we could say. First of these RTOs for IoT applications, and Contiki, then LightOS, then RiotOS. So RIoT-OS, you can say it like that. Then Android is also there for IoT applications. Then firmware, if you take the case of your mobile phone example. So mobile phone has the Android operating system, plus it has some custom software which is being programmed by your device manufacturer, say for Samsung or Oppo, whatever the company which you use. They have a custom software which is burned into this ROM. It resides there, and sometimes you'll be able to update it as well if it is within your warranty period. All those things over there, updates, OT updates could be taken. Okay, so that's firmware. Then you have applications, various applications which the user uses to which runs on top of these operating systems. Okay, the apps or anything which you call it as the applications. Then middleware, as we mentioned earlier, it's in the IoT architecture. It is acting as the interface between these applications and your hardware. Okay, so you have different middleware applications. Say your open source applications are there: Open IoT, Eclipse IoT, Zeta, ThinkSpoon, Fireware. All those things are middlewares. So say this, I've clubbed all these things into the one particular visual. It's much more easier to remember this thing. Probably TinyOS is their Android. This is very familiar to all of us. So this Riot, then Contiki, then this is for yeah, This is the 5ware. This is Device Hub, Things IoT, Eclipse IoT. This is by Huawei. Huawei's LightOS. Yeah, this is LightOS. So this is the logo for LightOS. LightOS. The Huawei has brought out an open source standard for LightOS. This is LightOS. Okay, and then Device Hive. All those things are middlewares. Eclipse IoT, all the Open IoT, Zeta are all middlewares, right? So the next thing is, so we covered both the hardware as well as software aspects, the communication aspects, sensing and identification. Next we come to services. Services, say different services are provided by IoT. So this is, you could say, identity related services. So mapping objects into the virtual world. Example, you use this thing usually in your logistics, say containers, your shipping, your Amazon does really use it. You are tracking your package. How do you track? You have a code which is scanned here, there. As for instance, you have ordered a new mobile phone. It is sent from Bangalore, and you can track it is reaching the hub. It is going there. It is going to Delhi. Sometimes it happens. Once in a while it happens. The package destined for Trivandrum goes to Delhi and comes back. Some reason, but it usually doesn't happen. It goes to from Bangalore to Cochin and Cochin to Alleppey somewhere. So that's the way it reaches usually. So so this is identifying. The logistics makes a lot of use of this. The information aggregation services. This is what we typically use in your health field, health IoT applications. So here what you see here is a data acquisition system, patient data acquisition system. It can connect to the internet. It's a Maximo Radical 7. It's a very handy thing. So you see the user just putting it just like a big smartphone there. It just plugs into the patient. It shows the vital signals, all those things. So the smart grid. Smart grid is something which really is hasn't really fully happened. It promises to help the consumer a lot, but I don't think it would be. It will help the companies, the distribution companies, much better. So anyway, the collaborative aware services. So here is where the machine-to-machine communication takes place. The devices will talk among themselves. M2M communication. Machines, the devices in your homes will talk about things, and they will provide you a consolidated data. Maybe you'll use a phone to see the status of different devices. So then ubiquitous services. Ubiquitous services is something which is a paradigm defined like anything, anytime, anywhere. Services. So you say that internet is everywhere, just like that in future. Every services, so collaborative services, you will walk on the road, you will see personalized advertisements, all those things. That's going to happen in the future. So that's happening also in some places at least. Okay, so that is the services. Then the semantics is really the way in which you extract information, extract knowledge from machines to provide the different services. Say basically it's the programming, the programming aspect, the queries. Say we might, at least some of you might have been exposed to SQL, structured query language. So same way, you have semantics. You need to send the correct query to get the correct resource. So different frameworks are defined. What is RDF, other is OWL, and much more efficient techniques do exist. So the EXI format is much more power efficient as well as resource efficient way for IoT applications. Okay, so that's regarding the semantics involved in IoT. So extracting the information, so analyzing the data provided by the device. When, say you send a query, send me the temperature in room 25, room number 25. So the temperature, how you put a query to the machine. So and that has to happen in a IoT environment. So efficient tools are provided. Okay, so efficient formats are provided. Okay, standards. Coming to standards. Okay, so standards, are we together? Yes, in the class? Yes, let me just turn on the charger. Okay, right. So so this is a very well-known thing. Who won finally? Who won? Who won this battle? Who won this war? It was not a battle. It was rather a very publicity stunt. Who won? Hello? Tesla finally won the thing, right? Tesla won the race. So, in fact, that was it was one of the first wars in the history of technology, the standards. Okay, so we need standards for these key reasons, these three reasons. There may be several other reasons. We could talk a lot about standards, but these three key reasons are why we need standards for IoT. Okay, you can't just plug in a network cable straight into an Apple and expect it to be connected to the internet. You need to clearly define what is the thing, how, so that different manufacturers, the cables made, or the devices, the equipments made by the different manufacturers are interoperable. Say you dump an equipment made by a Chinese vendor and take equipment made by an Indian vendor, they should be interoperable. There shouldn't be any change. Security and reliability are also key things of this standardization process. So we are more bothered about privacy, security, all those things much more than ever. As more and more devices are getting connected to the internet, we are more bothered about that. Okay, so different aspects to the standardization process. So you have standards which are developed by the typical standard organizations. You have IEEE, IETF. These logos are there, IETF, IEEE, all those people are there. They are the world known bodies. ETSI, similar to ETSI, we have a telecommunication standards development institute, TDSI, in India, very recently formed. It's related to all these. It's a close map of closely following this ETSI things. And W3C, so World Wide Web Consortium. Then there are industrial alliances, groups, say the LoRa Alliance or the Open Connectivity Foundation, Industrial Internet Consortium. They come up with the initiative, the Thread Alliance, the Thread Group. Thread Group is really coming up. It has support of several industries, Samsung, all those things. So alliances are some way to come up with standards, or there may not be standards, but rather there could be some agreement as to what these things are, and we'll have this thing. And finally, some of them become standards, de facto standards, like so that is, not all standards are made by IEEE. There is nothing like the electrical code, say for internet. There are a lot of disagreements. Even in the electrical domain, we'll see you have different types of starting with the voltages in different countries, as well as the plugs, the shapes and sizes of plugs, all those things we have dissimilarities. So there is no, the same thing applies to internet and related things, and telecommunication as well. Okay, so we'll have this four categories. So we'll expose you to quite a few of these things, and we'll discuss what really it means. Okay, this is we'll say there are something which is called as application protocols. Then you have service discovery protocols, which allows you to identify device. So DNS, you might have heard about this DNS, Google DNS. So all those DNS, domain name service. So basically it's related to identifying something like that. We'll totally skip this topic because it takes some amount of time to explain you the concepts related to this, but you could read about this DNS. Okay, I may leave some material on DNS maybe, then so I can share some material probably. So we'll see these three protocols, application protocols. Then we'll see some of these infrastructure protocols, miscellaneous protocols. You can do a reading about this. So okay, so if time permits, we can have a discussion. So this is the 4 categories. This is a summary of these IoT protocols. You have application protocols, service discovery protocols, infrastructure protocols, and you could say miscellaneous protocols. So in this, how do you make a distinction of these things are that the application protocols are closely related to the user, right? The service discovery protocols are one level behind, which is in the machine domain. The infrastructure protocols are further down. These are mainly concerned with the communication aspect. So whether it is Zigbee or Z-Wave or LT, 5G, 4G, all those things are purely the communication aspect. You can say like that. That's why they are being classified as infrastructure protocols. And then there are miscellaneous protocols, right? Are we together? Right. I expect only Professor Sindhu is responding, right? Rest of the people are there. I suppose they are there, right? More people have joined as well, right? So, so this we'll talk about the message queue, telemetry transport, MQTT. So there is no queue in this message MQTT. There is no queue. There is actually this MQTT was a standard which was a line of products which was sold by IBM. They used to have a, just like you say, Surf Excel, like that. Excel is the product. So it's a line of products, Surf Excel. So so when these two guys, they wanted to have this telemetry systems for monitoring oil pipelines. So they had satellite links, but they were very expensive at that time. But they need to acquire this data from the status of this oil pipelines, which used to run through remote areas, and they wanted to connect it to a satellite network. So they used this message queue MQTT protocol, message queue telemetry transport. The word telemetry, tele means distance and metry means measuring. So transporting the measured value, that's what. Then there is no queue there. They just named it like that. So this is ideally suited for low bandwidth environments. Low bandwidth in the sense internet is poor. You can consider data rate is very low. That is what the bandwidth കുറവാണെന്ന് നമ്മൾ പറയും. We often say bandwidth is less. What we understand what we really mean. It means your very low data rates are involved in this. So it basically works on something which is called as a publish subscribe model. Say for instance, you want to we can have an analogy with the cable TV. Suppose you want to watch the cartoons. You will tune into that particular channel, Nick Jr. for instance, and you want to watch the show which is running on there. You want to watch news, so you subscribe to that channel. Per pack, if you subscribe to a particular pack, you will get cinemas. You will subscribe to a particular bouquet or the base pack or the Malayalam gold pack. All those things you will get a particular channel in your thing. And so that will be available in your set-top box, and you can tune into that. Same model is what we use in the MQTT. Basically, here there is something which is called as a broker, and they are clients. So clients, you could say there are two types of clients. So some clients they publish. Some clients they subscribe. a client could serve as both the publisher as well as a subscriber. I'll explain this case later. And then there is something which is called as a broker, or you can call it a server. So this is a broker. So this particular scenario, I'll just illustrate this thing. This particular scenario, there is a temperature sensor there, which is publishing something called as a topic which is called as a sensor. You can say this is the channel name, Asianet News. I have no affiliations or anything towards Asianet News. I am just a user of Asianet News. That's what. I'm just whatever came into my mind. You could have replaced it with any channel. Okay. So temperature. It will publish the temperature values to the topic temperature. And these clients, so you have this clients could subscribe to this topic temperature. So broker is something which handles all these things. Broker is like a exchange which does all these, gets all this information, and it will just filter these messages, arrange these messages based on the topic, and whenever it publishes the status, at some time it will publish, or it would have the previous history values would be there. If anyone subscribes to this topic, they'll get an input. They'll get a message. Say there is a topic which is published as temperature, and it has received a new update, which is the temperature is 24 degrees centigrade. So the clients will subscribe to these topics. Some clients will just publish topics. Say this is one model. There could be another way. You have a bulb. You could bulb has to say, for instance, a smart bulb. Smart bulb, it has to check whether there is what is the light condition there. Street light. It has to turn on when it becomes night. So it has to monitor the ambient light, and when it becomes dark, it has to turn on. So it is acting as both a sensor. It will just publish the light conditions, I mean the ambient light conditions, whether it is dark or not, to the broker. And then there is some other device which is used to control this light. Maybe another control center from where you send a command to this device telling that you turn on the light. So this is acting as both publisher. The bulb in this case is both acting as publisher. It publishes the ambient light information. Along with that, it also receives commands from somewhere, which is some device which is connected to the internet. Say maybe there is a control center where you have a microcontroller, or Raspberry Pi, for instance, which is programmed to turn on light when the ambient light conditions become this level. So that's there could be devices which serve as both a publisher as well as a subscriber. Both these could be there. So this is the simplest way in which you could define MQTT. You could have much more the level above, where you have both the subscribe as well as publisher models working on the same device. Okay, right. So the brokers usually do not store messages. They don't have store messages. They just they can be configured. So you can have the different public MQTT brokers are there. One most common MQTT broker is Mosquitto. Mosquitto is the most common MQTT broker. So that is you could just MQTT Mosquitto. You could just search Mosquitto. Yes, Mosquitto. You heard me correctly. It is Mosquitto, and you could just search for this, or else you could use. There are plenty of tutorials available how to use MQTT Mosquitto service. You could configure an MQTT broker on a Raspberry Pi in your home and see on a local IP. There also you have plenty of resources. I am told there is a session on MQTT demo on the last day. Do attend that. Okay. So that is MQTT basically it's a connection oriented protocol. It is what is a connection oriented protocol means. It makes the best effort to get the data to the receiver. That will be the best, simplest definition you could say. So if you are sending a data from point A to point B, the TCP protocol makes the best effort to get it there. It will ensure that if there is some loss, it will make a retransmission. All those things are there. So it is not a push. It's not a request response service. Rather, it is a push based service. So you publish things. So you publish as well as then someone subscribes. So it's pushed to the broker and subscribers receive the updates. It's not the model like HTTP. Say HTTP, if you just say you are typing the name of the site, say www.google.com, press enter. There is behind the scenes there is a domain name resolution service, DNS service, which is working to translate all those things into the addresses. Then it's going to Google and it is fetching that page, and that is a request. You are putting a request to get google.com, and the response comes from the Google server. That's a request response model that is usually used in HTTP. Here MQTT uses a push service, so publish subscribe service model, right? And security is very aspect of this thing. You have a TLS encryption. That's the thing. You could have passwords at the application level, or else still better, if you want to have security at the network level, you can go for virtual private networks for the broker to gateway connection. You could have all these devices connected to a gateway, and gateway is connected to gateway is connected to right. I thought we lost the link. Are we there? Yes. Yeah, right. Thanks. Right. So this is MQTT. So this is a much more. This is a very suitable thing for different scenarios. Okay. Then there is something which is called the CoAP, Constraint Application Protocol. Constraint Application Protocol. It has been designed keeping in mind requirements of M2M communication, say, where you have the ultimate IoT devices have very low memory as well as low computation power. So they are not unable to run the full HTTP protocol or whatever, but you could provide something in the form of it is called as a REST internet. So REST functionality, REST. So representational state transfer, REST internet. So you just remember these terms. So even if you have we are not going to fully in details about these things, but you could look up if you are interested. REST internet, REST internet. So just basically, just as I explained earlier, like HTTP, where it is a request response model, the REST internet also works using such things, say get, put, post, delete, such resources, it access resources using such semantics. You can say like that, such tools. Okay, such commands, get, put, post, delete, all those things. And it uses UDP. UDP is user datagram protocol. So user datagram protocol is a transport layer protocol in the IP suite. Just like TCP, this is another protocol. Transmission control protocol is there, and user datagram protocol. User datagram protocol is used with the best example where we use user datagram protocol on the internet is YouTube. The variant of UDP is used. Your streaming media, you're watching a movie or a news, Asianet news over the internet, live coverage. I mean live news, not the recorded one, live one. Sometimes due to net some glitch comes, you lose 1 or 2 frames. You are not going to get back those things. You will just lose that moments. That's what happens usually, right? That is because it runs on UDP. UDP does not have a mechanism to retransmit the lost packets or lost frames. But on the other hand, TCP has mechanisms to do that. Transmission control protocols have protocol has mechanisms to make retransmissions of lost packets. That's what it depends on the application where you need. It depends on the application. You use either TCP or UDP. There are various other variants are also there, right? Security, it is again TLS and datagram. So AES is also provided. So that is datagram transport layer security. That's what. So this is the typical model in the CoAP. You send a request. So there is a thermostat which provides a temperature condition in 2 rooms, in the living room and the bedroom. And here the CoAP is putting a request, and that gets a request. So request is in this format. This is the protocol name, and just like HTTP, here it is CoAP / my home .in / this. So you have the port number, and you say this is a device. So this is a device, and get the temperature, the topic or the parameter, and you get a response. So that is get and post. That is what this is for constrained environment. So this is really a very good protocol for IoT applications, right? I hope this is clear. The idea should be clear with this. So again, coming to this is XMPP. So this is extensible message presence protocol. So it's instant message standard. Basically, it is independent of the operating system, and it is having a lot of secure features. This is particular protocol which will be a very clearly driver in case of Internet of Things in the future. This is an IETF standard. IETF is Internet Engineering Task Force. So this is one of the bodies which decides a lot of things. Decides in the sense they bring out RFCs, requests for comments. You say, well, if you search the keyword RFC, request for comments. So, and people can comment on that. Anyone with the they can take part in the RFCs, provided they have some standing in the technology domain, and they can comment on that, and they formally bring out the RFCs. So it's a sort of standard, standard for the things related to internet. IETF has RFCs on Internet of Things right now. The CDAC Trivandrum is working on RFCs for IoT, a form of some specific small area of the Internet of Things domain. Okay, right. So they are participating in that particular group. So basically it is a client server model. So they communicate. There is an XMPP server, and the clients will communicate to the server through a TCP connection. So it's a reliable connection, and then they communicate via the TCP link. Okay, right. The clients will not directly communicate with each other, rather through intermediate servers. That's why a client server client. So if this client has to communicate with this, it has to do with through the XMPP server. So this is on XML streams. So do read about this thing. So I'll try to skip off these things because it involves some sort of programming things, but there are services which do use XMPP, say your Google Cloud Print, then the Firebase Cloud Messenger. So Google Firebase is really a very good tool to get publish your data on the internet, IoT device data on the internet. Okay, right. So this coming to this, you have Logitech Harmony Hub. So it's just search for this. It's a home or smart home control or home automation, all those things. It's a lot of companies are participating in this initiative. Logitech Harmony Hub. Okay. Right. So these are using XMPP. So XMPP will be a driving factor in the Internet of Things area in the coming years. And Google Firebase. Right. So comparison. This is one particular variant which we didn't mention. This is for sensor net, MQTT for sensor networks, that is SN. That is what the transport protocols are outlined here. TCP, CoAP is using UDP, whereas HTTP is there always. RESTful internet is only provided by CoAP. Rest of the security, that is datagram transport layer security, others provide SSL, secure socket layer. So security is very significant thing, whether when we roll out a protocol for use, especially for internet applications. This is very key aspect for this. And the header, the communication header size, that's also the if you are sending a message, you need some control headers, address field, all those things, how much bytes it occupies. That's what the header says, right? So then we come to something which is called as a LoRa. So we are nearly 70% of this discussion. You have to ask me any specific queries you can ask, or we'll continue. We'll wind up on time. That's what I feel. Okay. So you have any specific queries? Shall we move forward with this? Right. Okay. So LoRa is an abbreviation for something which is called as a long range. Long range is what do you say? It's a spread spectrum technology. We are familiar with spread spectrum technology. In fact, now CDMA is a form of spread spectrum technology. CDMA, yeah. CDMA phone, whatever. Spread spectrum, what it does is that you have, for instance, your voice signal or your electrical signal. This is spread over the entire available frequency bandwidth. So that's a basic thing. So it was a military grade technology, and it has been commercialized. It has been released into public domain. And specific spectrum has been allocated for commercial CDMA services, and they use it. So LoRa also uses a similar form of spread spectrum technology. It's called chirp spread spectrum, CSS. Okay, and LoRa says it's very low power. Is required for LoRa devices, say ideally few microwatts. And if you have a AA cell, and say, for instance, I'm just giving an example, a AA cell could last for 1 year, on a 1 year or more, even more than that of a on a LoRa device. For instance, a sensor, a temperature sensor with this model. It depends on various other parameters, how often you turn on that device to acquire the temperature, all those things. But it is having it is very much power efficient form of communication. Power efficiency means you will finally end up with low data rates. Low data rates, that's what. You will have to sacrifice something. And one important aspect of LoRa is it is secure. It is having AES 128 encryption. 128 AES 128 encryption is very secure. It is in fact used by the US government also to encrypt data. So what is encryption? Encryption basically means you have, for instance, you have information to be sent. You will have this encryption key, and you will perform some mathematical operation with this encryption key, and you will send it. At the other end, you will have to use the same encryption key to decipher it, to get back the original messages. The one important thing of LoRa is that LoRa devices can be mobile. So they could be put on a truck, containers, the shipping containers and all those things. You can monitor, right? So the key here is that it's not the LoRa as such is not a open source protocol, rather it's a proprietary protocol. proprietary protocol owned by a company which is called as Semtech. Semtech is a company which owns this LoRa protocol. And on top of that, you have designed, so LoRa clearly defines the physical layer protocol, the LoRa technology. This how they do all this modulation, spread spectrum, all those things. It is not released into public domain by Semtech. They have this LoRa device which is licensed to different manufacturers, and they can make LoRa chips for use in for this LoRa modulation devices for use in different devices. And patent and royalty has to be given to Semtech. They are just it's not an open source technology. On top of this LoRa, you have built up something which is called as a LoRaWAN, LoRa wide area network. We'll talk about it. So it is LoRa, as you see, it is having a very large range, but the bandwidth available is lesser. So the markets are different. The Wi-Fi, Bluetooth, all those things are having high data rates, but the range is less. The cellular is the best possible case. The range is yeah, it depends on the network, right? Is really it depends on it. You can't use cellular services everywhere. You have various parts of the country where the cellular services are not available, 4G, 3G, even your 2G services are not available. But LoRa can go across that. It can go to forest, it can go to anywhere. You are not bound by any licenses of the spectrum also. LoRa works in the unlicensed band. So it uses this 867 megahertz band in India. It's an unlicensed band. You don't need any license there to operate LoRa devices. So bands vary. So if you're planning to buy a LoRa device, make sure it is suited for this band. You are using in India, you have to use this thing. So it is having a data rate of 27 kilobits per second. You are not going to transmit any video or audio using LoRa. It is a very low data rate thing. You are going to send control data, sensor data, all those things. That's what really matters. You are not going to send a music file over a LoRa network. You are going to check the status of a switch, you can check the status of sensors, all those things, and send it on a LoRa network. You can't think of sending a big file over a LoRa network. I don't think so. It will happen, right? So there are two things. One is the LoRaWAN and the LoRa. So LoRa is a proprietary physical standard protocol which is owned by Semtech. The LoRaWAN is an open source standard. So LoRaWAN clearly defines LoRaWAN has been to an extent standardized by some people which is called as a LoRa Alliance. So it is an alliance of various companies including Semtech, which has been formed to popularize LoRa, and this defines the application layer and the medium access control layer. So this is the RF layer, which is clearly the different country level frequencies. So 867, 865, 867, that is India. Then US, Europe, all those in the RF layer, that is there. Then you have the physical layer, which is defined by the LoRa standards. LoRa is proprietary by Semtech. On top of that, the LoRaWAN, clearly it's an open source thing, which is defining the different classes of devices, medium access control layer, and the application layer. So there is some distinction between LoRa and LoRaWAN. So LoRa is the physical layer, which is a proprietary thing, whereas the LoRaWAN is utilizing the LoRa devices to communicate over a wide area network, LoRaWAN. Okay, so this is an open source thing. You have a whole environment, right? Yes, I found something in the chat box, right? Right. Okay, let it be. So so this is the LoRa protocol. So the basic typical architecture of a LoRa network is like this. So you have the different devices. You say your sensors, meters, smart industrial devices, all those things. This link is bidirectional. You can send as well as receive data, and you have the LoRa gateways which send and receive data from this devices, the end LoRa device. So these devices will have this LoRa chip there, which can communicate over this wireless network on 867 megahertz. The chirp spectrum CSS modulated signal goes over this link. This is not a wired connection, whereas it is a wireless connection on 867 megahertz. So it goes to the LoRa gateway. So a LoRa gateway, you can consider it as just like your Wi-Fi router, right? And it can accept connections from different LoRa devices and LoRa enabled devices, and a device could connect to more than one gateway if there are different gateways. That's what. And the gateways will send it to your will identify the duplicates, and pass on the information to the network server. Only the single. So this, in this case, there are duplicates. This particular smart marking system is communicating to two gateways, the same info. So the gateway identifies the duplicate information and sends only the one of them to the network server. And here at the other end, you have the application servers. Say the user accesses this information. So this is the typical architecture of the LoRa WAN. And here you have proprietary LoRa protocol devices there. Then you have the gateways, and finally, so this part is a LoRa WAN which is open source. Here you have some proprietary chips there. Maybe in future LoRa will also be a LoRa technology as such will be released into public domain. So you will anyway. This is the aspects whatever we mentioned just now. So the one key aspect is that this devices cannot communicate to each other. There is no machine to machine, device to device communication. Rather, they could communicate only via the gateway. That is one key aspect. So if there is no device, they can't form a mesh network or anything. Rather, there is only communication via the gateway. It is one feature of LoRa. It is for security as well as the coordination. So this is some applications of the LoRa. So this is a LoRa device which is commonly, so this is on a ESP chip, and you have the LoRa module also mounted on that with a display also, right? Then you have the LoRa antenna mounted on top of a building. This is in a field. It's a LoRa device which could communicate to a remote gateway. So maybe it might be 10 kilometers away or 40 kilometers away. It depends on various factors, environmental factors or the propagation factors, all those things. So this particular link is how you can use something using RIK 831 gateway, LoRa gateway, and you can use a Raspberry Pi and use it to set up your home, set up a LoRa gateway in your college or your home. You can make an antenna also of this form using copper wire. You can have tried. There are several people trying, several private people who are trying this, because this is an unlicensed thing. You can try it. Say this is a situation in Trivandrum. You have multiple gateways, LoRa gateways there. One is this is in CDAC. This is somewhere around Keshavasapuram. Then there is in these two gateways are for IC4s in Technopark. There are other gateways as well. So this providing considerable. This is the range. This is using this community, the TTN Things Network. If you just search for TTN, the Things Network. Things Network is an open source aggregation of this LoRa devices. So you can register, form a community. There are similar communities in Cochin as well. So LoRa commercial services also exist. So Tata Communications, they have rolled out a pan-India LoRa network. Then there is a Senra, which is rolled out a pan-India network. They have presence in Trivandrum, all those things. So this is having a lot of potential, especially smart metering, logistics, all those things. So India also is on the LoRa map. So we are commercializing it. So that is not a technology in the book, rather it is being rolled out in a commercial way also. It is much more cost effective than the license spectrum, because it is, you needn't pay the spectrum charges, rather it is a unlicensed spectrum, 867 megahertz. So that is LoRa. Then the narrowband Internet of Things. Narrowband Internet of Things is operating using your LTE standards, your 4G, 5G, all those things. But it is using much smaller bandwidth than the traditional thing, traditional what do you say, 4G thing, LTEs networks. So 200 kilobits per second. So you require licensed spectrum for this narrowband Internet of Things. There are narrowband Internet of Things applications, use energy meters, LoRa based energy meters, all those things, smart energy meters, they exist. Commercial products do exist. So smart metering using LoRa or smart metering using narrowband Internet of Things is not a is a commercial thing, rather. This particular device, it could switch to Ethernet, it could use GPRS, it could use to what do you say, CDMA connections, narrowband internet, anything. Various flexibilities are provided by this thing. This is exclusively LoRa. Smart metering using is a single phase energy meter, right? Again, this is the narrowband Internet of Things. Okay, so this is narrowband Internet of Things over satellite. So this is jointly with the BSNL and a company which is called as Skylo. It's an Indian company. They have this service which provides uses the satellite network of the BSNL, and they have a device which is called as a Skylo. Skylo is a small hub, like it's a small thing like set-top box. It could interface to your mobile phone, all those things, by Bluetooth, Wi-Fi, Zigbee, all those things, and it could connect to the satellite network. And this is basically over what do you say, this is using this narrowband Internet of Things. So it provides updates to fishermen. It could be used, it could monitor train on real time. It could be used in disaster management situations. So this, for instance, the fishermen could be given updates on the cyclone, on the availability of fish in particular area of the sea. All those things could be provided by this thing. So this is a commercial service which has been launched by BSNL. It's available across India, right? Then another infrastructure protocol is Sigfox. Sigfox is also operating in the unlicensed band. It is not really caught up the market. It is using the cellular services to communicate. So the basic architecture is that you have all these devices, then you will talk to the Sigfox base stations over a wireless link on the unlicensed band. But from here you require a cell phone link, cell phone connection, cellular connection. The backhaul is either 3G or anything. Any backhaul network is required to for the rest of the steps, right? That is Sigfox. Then 6LoWPAN is really using IPv6 over low power wireless area networks. So this is having what do you say, low bandwidth connections, so 250 kilobits per second, but it consumes almost 1% of the power consumed by IEEE 802.11. That is your Wi-Fi devices. Very less power compared to your Wi-Fi devices, right? If you see the protocol side here, it has a lot of the IEEE has brought out a standard for IEEE 802.15.4. standard for low power personal area network. Your Zigbee, all those things are direct outcomes of this. Here we have more concerns with the power management. We try to use power efficient protocols for each of these layers. So that is defined in this particular standard. Here we see how this is used. You have a bulb, then a low power WAN connection to a low power WAN coordinator. You have a switch, all those things connected, and at the edge you have a low power WAN router which is connecting to the internet. So chips are available. The chips which implement low power WAN protocols are available commercially. So they could have in future we have more devices. We'll have more devices based on the 6 low power WAN for home automation, industrial control, and all those things. Zigbee. Zigbee is a very familiar protocol. Zigbee Pro is the latest in that, and it's as a good data rate, 250 kilobits per second, but the range is 100 meters max. Different architectures are there. Different architectures we'll see in the next slide, and it is in the unlicensed spectrum, and also 2.4 gigahertz. That is your that is also an unlicensed band. Your 2.4 gigahertz is your Wi-Fi frequency band. 2.4, 5 giga, all those things are Wi-Fi router frequencies, sir. That is, it is directly from this Wi-Fi low power personal area network standard 802.154. AES 128-bit encryption. So this is Zigbee coordinators will be there. There will be a Zigbee routers and the end device. So this is the basic architecture. And these are wireless. Zigbee to Zigbee networks, they are wireless, whereas this is on a wired connection. The problem with Zigbee is that if Zigbee has to communicate with the IP device, it is not possible. It's a difficult thing. Zigbee devices, enabled devices can communicate with each other. So to integrate with the internet, Zigbee has gone one step further, and they have modifications in the Zigbee protocol, and IP for Zigbee that has happened, and that is really going to allow Zigbee use in the Internet of Things domain. So other than that, Zigbee is has a lot of potential in terms of data. So that is there. Now we come to nearly the concluding part of this. So that is IoT analytics. With all these data gathered, all those things, we need to analyze them. We have different tools. Actually, the web-based, the cloud-based tools are available. You have the Azure, which is the Microsoft Azure. That is one platform. Then AWS, Amazon Web Services IoT chain, which is there. Then Google IoT Architecture, all those things. Then there is a Xenonify IoT Architecture. So this has different tools to allow you to do different tasks. So that is IoT analytics. So applying data analytic tools to all these data gathered and making some sense of what we have gathered. That is what. Then there is something, another thing which is going to drive the future is the edge computing. Say traditionally you acquire data from the devices and you transmit it to via some communication link to the end server where you process it, and then you send the control back, some commands back. So, but edge computing paradigm is to provide this computation at the device level itself, closer to the device, or maybe even at the device. Say for instance, in a self-driving car, you need to take decisions there on board. So you are providing computing on closer to where the sensor is. You are not going to send all the data to the server. Rather, you will do a lot of processing as well as the decision making at the device level itself, at the operation field itself, right? Now another aspect which is going to drive IoT is the blockchain technology. So blockchain technology is familiar to you. Blockchain is basically you are say for instance, it could be involving anything, right? Rather the data, cryptocurrency, bitcoins, it could be records, anything. You need to make sure it is authentic. So for instance, someone is requesting a transaction, say a Google Pay transaction. So this transaction is related to a peer of computers, a group of computers, your network of computers, peer-to-peer network. And say this is validating. They will check the ledgers, you can say like that, and authenticate that this particular user is authenticated to make this particular transaction. And this transaction, once it is authenticated, it is added to the existing ledger. So that is a block, the blockchain. It's a chain of blocks. And once this is there, again, so you're making a transaction, like you are going to make a transfer of say 200 rupees to make a mobile recharge. So that is authenticated. You have to make sure that is the person. He has the authentication to do that. So this is going to ensure the reliability of the data transfer, reliability of the transaction. So IoT could benefit from blockchain technology. It will build trust. It will make the system much more secure. Whatever data you have gathered from your patient, from your hospital environment, you can ensure that it is a reliable thing. It is going to do things. Transactions could become faster. You are not going to make any soft copy or hard copies of the things in future. You can be very sure this is reliable because it's a public. It's on a peer of computers, peer group. It's a peer-to-peer network. The data is stored in a peer-to-peer network, and it has been validated, right? So that is there, right? Again, coming to this is the security aspect related to IoT. Different IoT has inherent flaws. Potential weaknesses are there in different aspects. You have the code, which is maybe open source or third party code. It's copy paste use. So that has potential for different security flaws. The cloud has flaws. Communication security, we mentioned there is AES 128, which is good enough. Then you passwords, policies, different say at the sensor level, you have physical security of the device is something which we can't ensure. Someone can go to the site and just damage the sensors which you have put there to acquire data. That is something something which can't be done from a computer, controlled from managed from a computer. You will have to ensure physical security, but other than that, you could ensure that your device has some measures to ensure that its firmware or the software which runs in your sensors, they are secure enough, they are some way not susceptible to manipulation by malicious people. So then the data security, the data privacy, all those things are key to this. So IoT has potential. So this is by Juniper Research. This particular infographic is from Juniper Research. So privacy issues are there. They could transmit information about the person. You would have heard very incidents where the Google Assistant or the Alexa has recorded conversations which are not related to its use, the personal conversations of people, all those things, and it has passed it on to some other person, emailed it, in fact. Again, hacking, that's always there. If you are talking about industrial internet, that will become a very serious problem in future. Then data mining by IoT service providers. Say, for instance, your insurance company could monitor how you drive the car, whether you do exercise, what all food you eat. Depending, your sensors are going to monitor all those things. They can mine this data. They can decide the insurance premium accordingly. That's what. Now, coming to more on the electrical side, you could use IoT for say some aspects like this, the tower inclination. Say you could put up sensors on top of that. In fact, there are uses. Say you have wireless power line sensors. So they could monitor various aspects. So you have sensors here, and then there is a controller, which communication hub is there. This is a pole mounted substation, a transformer, you say. So it is communicating to your distribution network. So they can get the status of the line. So they can monitor various components involved in the distribution side. The smart grid really its promises to provide the subscribers, the consumers, the ultimate benefit. But say it integrates your green energy, it integrates power stations, it integrates the distribution side, the end users, the consumers. Say this is the production side, all those things. So smart grid is going to connect a lot of things, and it says say it will be much more robust, it will be much more resilient to failures. You are able to get near real-time updates about the demand as well as supply side, and you could take decisions based on that. The billing side, people say the smart meters, smart energy meters, the consumers are going to benefit. I don't think so. They could be charged based on the peak usage. All those things are possible, and they could be given incentives for using green energy. They can sell energy, they can make energy and sell it to the grid. That's all possible. Smart metering, all those things can come up. So these are aspects which you will come across in this course. I hope there will be sessions on this, and some particular thing which really electrical engineers especially use as a SCADA. So SCADA has been extensively deployed in your electrical distribution as well as your generation side. Even KSEB has a SCADA network. So especially in the metros, say I think Trivandrum, Cochin has the SCADA network there. So they are able to monitor the real time at the control HMI, that is the human machine interface, where they can really monitor the generation side as well as the distribution side, and they could monitor remote line units could be monitored to see the load as well as different network parameters. But SCADA networks traditionally, they are really suited for an industrial environment, and Internet of Things is often seen as a competitor to SCADA, but I don't think it will be replaced. Internet of Things is not a replacement for SCADA. SCADA has a lot of potential, but SCADA networks typically, the flaw or a drawback of SCADA is that they acquire a lot of data. They have processed this data, displayed in the control room. They have access to historic data as well. Say the load values, the requirement values, for instance, in last month or next week, whatever, per previous week, those things are available. But despite all these things, the data analytics part, which is a strong point of Internet of Things, is not available in SCADA. But there are efforts to add this data analytics part, prediction part, the predicting, that's possible. Internet of Things components could be used. The problem here lies in this different paradigms where SCADA and IoT works. So IoT typically means everything is connected to the internet, but SCADA, basically they are firewall systems. Say due to security concerns, all these power grids networks are not connected to the public internet. They are air vacuumed. That's what we recently read about, the October 2020 grid failure in Bombay, where it seems malicious actors from outside, they tried to hack into the power grid. They caused a power outage in October 2020. So in Maharashtra. So that's really a sensitive matter to this. So this IoT means they need better secure systems which could be connected to the so that it could be used much more in the whatever you call it as Industry 4.0. Industry 4.0 is a technology which is really catching up. You will come across it in the sessions, I think on the third day. Okay. Then the future trends, harvesting energy from ambient sources, energy harvesting. So you could harvest energy even from the vibration of the glass on a window pane. So different ways are there to access it. You could the MEMS technology, micro electromechanical systems. That is a very key technology which is going to help in harvesting energy from different ambient sources like wind, thermal vibrations, solar, all those things. These are different, what do you say, aspects. So at the same time, your electronic devices are also consuming less power. In future, you have self-powered IoT devices. Self-powered IoT devices which will harvest energy from thermal or vibration. Say you have put up a sensor somewhere, it will find scavenge its own energy. It will get its own energy from the ambient environment, from the wind. Maybe the vibrations are picked up. It is you have put a sensor on a glass pane, and when the air moves, the wind moves, the blows over this pane, the vibrations would be used to store energy. There are energy harvester ICs. So this particular IC is BQ255 series. That is energy harvesting chip. So that is another thing. There is another aspect is nanosats for providing Internet of Things services. So these are located in low Earth orbit, say 400 kilometers above the Earth's surface, just like the International Space Station. So they are in low Earth orbits, and they'll be able to provide Internet of Things services anywhere across the globe, right? So what is this? What is this place? What is this place? What is this place? Anyone?
Mars.
Mars. Yeah.
Mars.
Yeah, it's Mars. We are going to Mars in very near future. We are going to Mars. Actually, we have stepped there. Last month we had people. We no, not people, rather this rover Perseverance rover going there, and it had all sorts of these sensors there. So we are going to. So this is going to drive technology. The Mars missions are all going to drive technology in a big way. So we are looking at sensors in deep space and acquiring data from deep space. All those things are really happening, and some fund resources you could use to learn Internet of Things and related things. You could go to Scratch. So those who are really afraid of programming, also having some aversion towards programming, could use this thing, Scratch. A really cool way to learn programming. And then you could have see Tinkercad. Tinkercad is a very interesting tool where you could try out various things. You have Arduino, all those things, models there. You could have sensors there. You could connect and make various things. It's a lot of tutorials also exist how to you do give a try. Okay, so that's it. You can have a discussion or feedback.
Anyone? Any doubt? Participants?
You can ask anything, so that whatever I could tell, I could share with you.
If there is any doubt, please unmute your mic.